Okay, are there any questions? Does everyone have the software running on their laptop, able to compile and get to the microcontroller? I'll go through another exercise today. The last time we actually had it using the printf through the debug, but it's a lot more convenient to actually have it print through the serial. It's an emulated serial terminal. And we'll set that up today so that you don't have to run in the debug configuration. You can just run it on the microcontroller and see the printf output. But if you don't have the software running on your computer at this point, we need to get that fixed as soon as possible. So you're using a Mac and then was able to run okay on the Mac. Is anyone else using a Mac? To get the software installed, okay? Okay. And then I've installed it on a Linux machine. I don't think I currently have it running on a Linux machine, but it runs under Linux as well. So, and then certainly under Windows is what I'm using here. This machine is really slow though. So today we're going to start talking about, move into chapter 3. So were there any issues on that programming? It was really a much of a programming assignment. Just ask to copy in the code and run it, right? That's a pseudo-random number generator. It's not a random number generator. So if you run it the same number of times, you should always get the same number, right? But every time you call it, you should get a different random number. And ideally, it would generate all numbers between 0 and 2 to the 32 minus 1, since it's a 32-bit random number generator. But mainly that exercise is just to ensure that you've got Code Composer Studio installed and you're able to compile and get stuff running on the microcontroller. Because that's pretty much what we'll be doing the rest of the semester. Okay, so chapter 3 is an intro to the ARM architecture. And there have been you guys are familiar with Intel, maybe you've seen some Motorola processors. ARM is a particular processor, okay? Doesn't use the same instructions as the Intel. So programs that you write for an Intel microprocessor will not run under the ARM. They have to be recompiled, okay, from source. The assembly language is completely different because the internals of the microprocessor are completely different. The machine code is completely different on these architectures. But again, the advantage of the high-level languages like C is, hopefully that you can write your C program on one machine and transfer the source over and recompile it. You get a version that runs the same on both machines. Can't take the machine code over, or the executable file over. Can't even do that between operating systems that run on the same like Intel processor. Linux machines won't run under Windows because they call different system libraries, even though it's the same processor. Completely different operating system. Okay. So the underlying operating system calls are completely different. But so we're going to spend some time in this chapter, next week or so, talking about the internals of the CortexM processor, which we're using. And different processors will have different types of registers, different names for the registers, different number of registers. But learning one architecture should help you at least have an understanding of other types of architectures. Ideally, if you're doing everything from C, you wouldn't care so much about the architecture. You wouldn't have to know the register names. don't call them directly. And you have to know something about the internals in order to actually access the various peripherals available on the microcontroller. But you don't have to know the architecture at the level we're going into. The program and assembly, you're working directly with the internal registers, right? You're not using variables. You have data stored in memory and move it from a location into a register and write it back to memory. But you have to have a deep understanding, actually, of how many registers there are. You have to have an understanding of how a function call works. You know, in C, it's pretty simple. You know, you have the function, the pass it parameters, and you get a result back, right? How does that happen, you know, underneath? How is that function call? How is that done at the machine code level? So, you know, ideally we'll get to the point where you'll be able to call a C function from assembly, or you'll be able to write functions in assembly that you can call from C. If you get to that point, you have a really good understanding of the architecture and then how the function parameter passing works. And that relies on using the stack quite a bit. So the CortexM microcontroller, I'm going to reproduce a figure that's in the text, so you wouldn't have to write it down if you don't want to, but as I'm writing it down, I'll talk about it. So there's a processor portion that has all of the, it does all the arithmetic, all the logic. You also have in the CortexM an instruction ROM. And then a separate data RAM. And this is another big difference between often microcontrollers and general purpose microprocessors, where, you know, in a microcontroller, we typically transfer a program into one type of memory, flash ROM here, so that when we turn off our microcontroller and then turn it back on, it'll start running that same program again. Everything that's in RAM is lost, but our program is preserved in ROM. General purpose microprocessors work differently. The operating system, all your programs are actually on hard disk. You know, our little microcontroller doesn't have a hard drive. But on our PCs, the programs actually reside on the drive when the machine is turned off. We turn the machine on, it starts loading the operating system from disk into memory. We run an application, you know, by clicking on it on the desktop. That executable file is transferred from disk into memory. So on the Intel processor, the same memory, RAM, is used to hold the instructions and the data. You know, it's all transferred from the hard drive into the same memory. We also have, so actually on this processor, there's a bus that's used to transfer instructions from flash ROM to the processor. So it's called the I-code bus. There's a separate system bus that's actually used for the data transfer between RAM and the processor. And then we also have input ports and output ports for interfacing to the outside world. And these also transfer data over the system bus. So input ports. In addition, microcontrollers typically have a lot of internal peripherals. So things like internal clocks, there's what's known as an interrupt controller, there's PWM generators, there are serial communication sections of the processor. These all communicate directly with the processor using a private peripheral bus. I'll define all these acronyms in just a minute, but that's PPB. There's a separate, what's called the decode bus. That's used for control, primarily by the debugger. And then finally, there's another bus that can be used by, actually let me show it, going between the input and output ports. It can be connected to the input and output ports. That's the Advanced High Performance Bus, or AHB. So this is the CortexM processor, or microcontroller. So it's pretty sophisticated, and there's a lot of, there's a 1,000-page manual that describes all of the internal peripherals, Each different section has all of these different registers, each with a different address and purpose. So we'll have our hands full this semester figuring out all the things that this microcontroller is capable of. But the good news is, once you learn how to program one microcontroller, you're well on your way to programming other microcontrollers, and they have completely different architectures. There are a lot of similarities between different microprocessors. We are going to learn to program in assembly, which assembly is painful. No one likes to program in assembly. It's hard, and you have to have a good understanding of the architectures, and very few people program in assembly anymore. Most people will program in C. There are a couple of instances where you have to program in an assembly. If the processor microcontroller has some special features that aren't available from C, okay, like Intel introduced some special instructions for support of multimedia, support processing video and audio. And they weren't directly available. You couldn't access those from C. There were no C language instructions to do that. So in order to access those special microprocessor instructions, you had to program in assembly. Fortunately, someone came along and wrote a library that you could then access from C, but that library had to be written in assembly. So that's one reason. Another reason is there are some sections when you're writing an operating system, typically when you're doing what's known as the kernel of the operating system, that has to be written in assembly, because that's where you have to deal directly with the registers that are inside the microcontroller. I guess the third reason is just to torture you, because I like to do that. So, but actually, if you know assembly, you have a good understanding of microcomputer architecture. I think I mentioned that the CortexM uses what's known as a Harvard architecture. Where there are separate data and instruction buses. The other type is what's known as the von Neumann architecture, where the same bus is used to transfer instructions and data. And again, that's the Intel. Most desktop, probably all desktop computer systems actually use the von Neumann architecture. The Harvard architecture is a little more common with microcontrollers, where there's typically a flash ROM where we load our program as opposed to having a hard drive that would hold all of our program. So just the I-code bus is used for instructions, to transfer instructions. The decode bus is for control, debugging. System bus is used for data transfer. And I didn't draw, there's an address bus going to all of these different purposes. We'll see that in just a minute when we look at the memory map. There's the private peripheral bus, or PPB, that's used to communicate, to pass information back and forth between the processor and internal peripherals. And then there's the advanced high performance bus, or AHB, and it's available for high-speed I/O. And in particular, it's used by the USB controller to transfer data back and forth between the processor. Every microprocessor has what's known, so this, I'm taking a look at what's inside this box in the upper left, the processor portion. Every microprocessor has what's known as a register stack, or sometimes it's called a register file. So let's see. The CortexM processor has actually 16 32-bit registers. These are all 32 bits. 0 through 12, there's 13 registers are general purpose registers. R13 is actually used as the stack pointer. There's actually it's actually two separate registers, but they're both accessed as register 13. It depends on which mode the processor's in, whether it's in main mode or process mode, executing an interrupt. R14 is what's called the link register. And then R15 is the program counter. So this is the 32-bit register file or stack. It's not a file like a file on a disk or anything like that. Okay, so I mentioned R0 through R12 are general purpose registers. R13 is the stack pointer. So as we start to program an assembly, the stack is kind of hidden from you in C, but all the local variables in a function are actually stored on the stack. We can at any time push a register value onto the stack. That the stack always points to an area of memory, an area of RAM. So we can push a value, so the stack pointer contains an address. to a particular location in RAM. We can push a particular register onto the stack, then it gets stored in data RAM. The stack pointer, the stack works down from highest address to lower addresses. So it's actually decremented, the value's pushed. The next time we push, the stack pointer's decremented again. All the pushes here are 32 bits. Actually, we'll see the stack pointer in this machine, it's actually, you have to push 2 registers at a time. Later, if you want to restore your registers, you pop the stack, which moves data from RAM back into the register. So the stack allows you to save data if you fill up all these registers, which is not uncommon. Start working with any arrays, longer arrays of 100 elements, 1,000 elements, are all going to be stored in RAM. Okay. In order to process those elements, you actually have to move them into a register, add them or whatever, and then write them back to memory. R14 is the link register and holds the return address in a function call. So you guys have programs have called functions, but you're in your main program, it's executing, you do a function call. The program counter gets loaded with the first instruction in that function. Now, when the function is done, we have to get back to the next instruction in our main program. Okay, so that the address of that next instruction is stored in the link register, so that when we do a return from the function, we go right back to the next instruction after the function call. So, get to a function call, program counter gets loaded with the first instruction, the address of the first instruction in that function. At the end of the function, we return back to the next instruction in our main program. That address is stored in this link register. And then finally, R15 is what's called the program counter. Or instruction counter. It contains the address of the next instruction to be executed by the processor. So, in this case, it would contain the address of the next instruction that's in flash ROM. So whatever we're doing, we do an addition. The next instruction is a move. That instruction pointer would have the address of that next instruction. So we get done with that addition, then that move instruction, which is here, gets loaded into the processor, and then we carry out that move instruction, and then the program counter is automatically incremented to the next address. Unless there's something like a function call, again, where we jump to another address, or there's an interrupt, and we have to go off and do carry out an interrupt, execute an interrupt routine. So the general purpose registers, again, they are not completely open. So every architecture has what's known as a procedure calling standard. So when you call a function, you pass parameters to that function, right? It could be 1 value, could be 10 values in that function call. How are those values actually passed to the processor? In C, we could actually pass 20 parameters. That would certainly be too many to store in these registers, right? Because we only have 12 general purpose registers. So how do we pass parameters to a function? Well, they could all be passed on the stack. And I don't know if you have a clear idea of what the stack is. It's an area of memory. But one way is, before we when we get to that function call, what happens at the assembly language level or machine language level, all those values then would be pushed onto the stack. Then we jump to the function. The function knows exactly how many parameters it's supposed to get passed, and then it would pop them off the stack and have them available. Well, it's a little more efficient to pass values directly in registers. Okay. So with the standard calling procedure for the ARM processor, registers 0 through 4 can be used for parameter passing. So 5 registers. So you have 5 parameters in your function call, and they would be passed directly in a register. If you have more than that, they're actually pushed on the stack. The function has to know that. It has to know that the first 5 parameters are directly available in those first 5 registers. Okay. And if it's expecting 6 input parameters, it knows it has to go out to the stack and get the 6th value. Okay. But there's a standard that's kind of arbitrary. We could have used all 12 to pass parameters, okay, or maybe just 2 registers, or maybe none and passed everything on the stack. It's a little more efficient to pass things directly in registers. Okay. So, but 0 through 4 you can use those as kind of for any purpose in your function call. You don't have to preserve their value, the contents. The other general purpose registers, 5 through 12, when you get done with the function call, they have to have the same values that they had at the start of the function call. They have to be preserved. So, well, what if you want to use them? Well, you have to push them onto the stack, use the register, and then restore the value from stack before the function call. And that's all part of the function calling standard that's used on the ARM processor. And we'll look at that in a little more detail later. Another important register is what's known as the status register or the program status register. Or the PSR. Actually, on this ARM microcontroller, it's 3 separate registers, but it does some magic. You can access them to one result. So the program status register has all this information about the results of various arithmetic or logic operations. Okay, so in C you want to see if one number is greater than another, or you want to check to see if something's equal to 0 or some value. How is that done at the assembly language level? Well, or machine language level. Well, in machine code, if you want to check to see if 2 numbers are equal, you have to you subtract them, and then if you get a 0, that 0 will actually set a flag in the program status register. Okay. So again, there's a lot of stuff going on at the C language level that translates into several machine code instructions. So this program status register, it's a 32-bit register. It has N, Z, C, V. These are typically called flags. C, I, T, T, C, I, T, and then ISR number. So this is 32 bits, as are all of these registers in this processor. So there's 0 to 31. So this one is actually, this portion is 2 bits. This is bits between 16 and 23 are unused. Here's 6 more bits of this. And then bit 9 is unused. And then there are bits 0 through 8. Those 9 bits form the ISR number. So these are called flag bits. If you do any arithmetic operation and you get a negative result, whether it's subtracting, adding, multiplying, dividing, if you get a negative result and you choose complement arithmetic, it sets this bit to 1. So there are various instructions that, if this bit is set, we can branch to a new location. So this is how all those if instructions that you use in C would ultimately be implemented in the machine at the machine code level. Z is used to indicate if there's a 0 result. Again, that's used for comparing two numbers. The way that's done in machine code level, you actually just subtract them. If the Z flag is set, that means they're equal. Or you can also tell if one's greater than the other because the N flag would be set accordingly. A C is the carry bit if you're doing an unsigned arithmetic operation. And the V is the signed carry. We have different machine language instructions that are used if we're working with signed numbers versus unsigned numbers. Q is the saturation bit. The ARM processor is actually capable of doing what's known as saturation arithmetic that, typically, when we add 1 to a value, it rolls over. We've seen that if we've got an 8-bit result, we get 255, we add 1, the register actually rolls over to 0. That's the standard way of doing that arithmetic. Well, this processor is actually capable of doing what's called saturated arithmetic, where you can restrict the range to 0 to 100. And then if you add 10 to 95, it would actually be clamped to 100. Okay, it doesn't roll over. The T is the thumb mode. So the ARM instruction set, there's actually 2 modes of operation. ARM CortexM only operates in thumb mode. It's a particular instruction set. So an interesting, what happens when you first turn on a computer? Well, the Intel processors are hardwired. There is a ROM in your computer on the motherboard. It holds what's called the BIOS or the UEFI instruction set, but there is a BIOS that's actually on your computer board. Because when you first turn it on, the microprocessor doesn't know how to read programs from disk or anything, right? So the processor has nothing in it. So it's got a particular address that's an address of ROM, and that's where the microprocessor gets the first instruction. Encoded in ROM are instructions on, well, this is how you read data from disk and things like that. So with the ARM processor, the first 32-bit word in ROM is used to initialize the location of the stack pointer. So that's going to that will point to some address in our data RAM. And the second 32-bit word, so I'm treating these as an nth array. So each one of these is 32 bits long. The second value is located into the program counter. And then the next instruction, our first instruction then would be loaded from ROM into our processor at that particular location. Okay. The last thing I'll mention, and then we'll look at another exercise here on is the memory map. Let me draw it over here. So our processor has 256K of flash memory and 60. And so this is at location 0x0000. I'm going to use a dot here just to separate. So that's a 32-bit address, but just to show you where the middle of the address is. And then 0x0003 dot. So one more than that would be 4 followed by 4 zeros. That should correspond to 256,000. And then there's a gap. RAM starts at 2,000 and then goes from the 2,000 dot 0, oops, FFFF. So again, that should correspond to 64,000 addresses there. And then there's a gap and the I/O ports. And that's from 400 to the last address here is so a fairly large address range for the I/O ports. And then there's the internal I/O or the internal peripherals. If you remind me, we've looked at that watchdog timer. There's a line in our code. Those are all macros that actually translate to addresses. They should translate, I believe, to addresses in this internal I/O range, because that watchdog timer is one of the internal peripherals. So when we pull up our program, we'll look at that. So we're using one particular version of this MSP 432 from TI. The main difference between the different variants is they have different amounts of RAM and ROM. You're going to pay more for a chip that has more memory in it. This is the layout for the particular microcontroller we're using. It has 256,000 bytes of flash ROM for our programs. So we can't actually run programs that are larger than that on this particular microcontroller. Fortunately, that's fairly large for microcontrollers, and it's limited to 64K of RAM, which is laughable by PC standards, right? You go out and buy a PC, you can't buy one today with less than 8 gigabytes of RAM, right? Or 12, 16 being kind of common now. This is 64,000 bytes of RAM, which, again, it's a lot for a microcontroller, not much for a desktop computer system. Okay. Any questions on that? So if you've got Code Composer Studio on your laptop, fire it up. This machine's so slow, I have to fire it up and give it about 10 minutes. So unfortunately, I already did that. So let me erase this section. So we got started last time using just the simple printf. And again, we've got this microcontroller. It doesn't have a display connected to it yet. You may have noticed we've got a little LCD display in your parts kit, but there's nothing connected to it yet. So, when it does something like a printf, and ultimately, unless you've got a display, you really don't use printf with your microcontrollers, right? It doesn't show output. Again, unless you have some little display, but a lot of applications, there's not a display available. So they've made life easy here. At least the first implementation of printf, if you run the processor in debug mode, it uses the debugger console, and you can see the output of the printf. That's nice, okay. But it only works when you're using the debugger. When you get ready to release your project, you're not going to run the controller in debug mode. You're going to load your application on it and run it. So there are a couple of different ways. In this microcontroller, it allows you to redirect printf, to an LCD display when we ultimately hook one up. But the first thing we're going to look at is actually redirecting printf output to the serial terminal. Okay, this microcontroller used to be you had separate serial ports on your computer that you could connect to various microcontrollers. Now we do things like we use what's called a virtual serial port that's part of the USB interface. And so when you connect your microcontroller up, it actually creates this virtual serial port. And we're going to access that. Okay. So what we're going to do, and I'll go through these steps again. So new Code Composer Studio project. And then here, make sure that this is the MSP 432P401R. That's the particular processor we're using. If you choose something else, it might have the same assembly language instructions, but it may have different peripherals. They may be at different addresses. It may have different amounts of RAM or ROM. It may or may not have a watchdog timer. So, it may compile, but it probably won't run on the particular microcontroller that we have. So I'm going to call this printf, and then UART, which is Universal Asynchronous Receiver Transmitter, which is another fancy name for a serial interface. And then finish. Okay. Now, again, what it does at this point is create just this dummy main for us. That looks like this. Actually, what we're going to do is import a couple files here that the textbook author provided, because he's already set up the UART for us. We will get there on what the code does, but right now we just want to be able to do printf and see the output. So actually delete, so right click on main.c, we're going to just delete this. That's the easiest thing to do at this point. And then right click on the project and say add files. Now, I don't know if you did this or not, but in this, if you follow those instructions, like the last thing you did was download this Valvano Valvano archive, and then you unzip that at some location. We're going to actually add files from that archive. So you want to browse to wherever you installed that. I put it in the same, under the TI directory. It doesn't have to be here. It can actually be anywhere. So Valvano where, and he's provided a lot of software to get us started. And then I think it's printf uart is the one you're looking for. Okay. And all we need here is the main program. So click on it. And then, at least in my window, it's got the UART-C and the UART-H. So hold the control key and then click on those. And it'll add all three. It says, do you want to copy them or link them? We want to copy them over. If we link them, it keeps them in the same location. And then any changes would make changes to the original source code. Okay? We don't want to change the original source code. Okay. If you take a look at main, you know, it's not, he's got a bunch of printfs in here. The UART.C sets up the UART. The only thing that you have to do to use this now is include this UART.H file. Now it's actually set, instead of doing debug, if you click on the little hammer, we're going to do a release version. Okay. You could do debug, but we'll do the release version. So preparing for build, okay. And then now project, build project. I got some errors. Okay, and it says there's an error in UART-C. If you click here, I don't know, the way he had his software set up, you can include just the msp.h file or the msp4032p401r file, but he's got this .inc. Get rid of that. And then try building again. I think that's the only error. Okay. Microcontroller here. Okay, so it looks like it built this time. And I swear there used to be a little triangle on here that I could just click and it would automatically load it on the processor, but I can't find that. But so the way I've been loading release versions, you go to the run menu and then say load, and then say select program to load. And then now you're going to have to browse to, you know, wherever this directory is. For mine's coming up in this TI Valvano, which is not where this is. So you're going to have to browse to wherever your workspace is. Mine was actually C users AR63 workspace version 10, and the printf uart, go into the release directory, and then select this printf uart file, and then open that and click OK. And hopefully now it's going to transfer to our microcontroller. Looks like it actually rebuilt. Takes a while. I think it's running now. The other thing that you need, though, it's still transferring. The other thing that you need is a terminal program. Now, I'll put a link to this up there if you don't have one. One that's free is called Putty. It's already installed on this machine. And you have to set up Putty so that it actually, Putty will do telnet, secure shell, but we want to do serial connection. The other thing, you'll have to figure out what COM port this thing is using. One way to do that, at least in Windows, this will work. Most of the time, I think it's going to be COM4. But if you right-click on this PC in File Explorer and say Properties, and then say Device Manager, and then look in the list, it should say somewhere ports. And then this is XDS 110 class application user UART. Mine says COM4 there. So yours may say some other COM port, but if you don't want to look at it, I would guess at this point just COM4. And then the other thing is you have to set the communication rate. It's 115/200, I think. You can give this a name and save it. I've already saved it as Launchpad. Okay, so you got 115/200 is actually the communication speed. I don't think you have to change anything else. But then you give this a name and then save it. But now we want to open this connection. You'll see that it's printing out a bunch of stuff. This is stuff that's being printed out from the microcontroller. If you reset the microcontroller, you'll see it starts printing out those numbers again. Okay. You'll see in the code in the main program that it's printing out a whole bunch of stuff here. After it starts, it prints out some stuff initially. Let's actually just comment this stuff out that's in the while loop so it doesn't print forever. And then project build. You'll see the process is still running here on the, I'm still waiting for it to build back in Code Composer Studio. Okay, fine, it says, and now from the run menu, load, it remembers the last load, and then printf UART. So after it loads, it should actually reset the microcontroller. I changed it so it just prints out the initial information. It doesn't print out this endless stream forever, at least I think I did. So once it finally transfers over, it will automatically reset. And just print out that initial information. Then now every time I reset the microcontroller, I'll see that output displayed. Then it goes into an input loop where it doesn't do anything. So now at least you don't have to run the things in debug mode. You'll have to get this terminal program or a terminal program. Does anyone use anything other than PuTTY? And everyone's TerraTerm. PuTTY's nice. It's free. So I'll put a link up to that if you don't have that. I don't know what they have for the Mac. I've used one under Linux. I don't know what it is. But you can use this now in run mode. Right? That's it. Okay. Okay, you also have to add two other files. So go back and say, yeah. And then are you in that same?
I didn't have that.
Also add the last and then
Yeah.
And this is when you have to go in there. Your C and get rid of the dot.
Run it.
See, thank you.
Yeah. Oh yeah, you don't have the microcontroller. And then there's you'll have to get some sort of terminal program for the Mac to connect to.
There's a terminal app, but I'm not really, I'll figure it out.
Okay. Yeah, this is not, this under Windows, this is not the latest version of this. So it looks like it's Code Composer Studio. So this is an older version of the software, so it's not going to be the same as what we see here. So, but whatever you did last semester, I think it's the same microcontroller. You might want to download the new software.
Excuse me?
Yeah. Every time you try to build, let me try and build.
It's going to take a while.
It always does.
Yesterday when I do homework, I used 4 months scissors. Is that matters?
You use what?
Like 4 months just one.
Yeah, I don't think that should matter. Let me sit down and see. Do you have class?
Yes, in 7 minutes.
Okay.
After class.
Yeah, I'll be available from 2 to 3. I have class again at 3, and then at 4.
Okay, and one more question. Here, it's E0004 and 0.
I think it should be 4 Fs instead of, yeah, it's in, I think that should be 4.fff.
4.FFF.
And let me check in the book.
Should that be E004 instead of E0004?
Yeah, I think that's, yeah, it shouldn't have 5 digits there. Oh, yeah, there's just, get rid of one of the zeros here.
Okay.
That's right. Yeah, you want to see me?
Yes.
Yep.
Are you available now, or?
Yep, I am. Let me actually shut it down. I think all this is still being recorded.